he's at Rice doing a postdoc. Senior media professor took my class a few years ago. And then now he's at Rice.
So can everybody hear me? All right. I'm really happy to be here. It's really nice. As Anat said, I graduated in 2016, and I have been away for almost 3 years. And it's really nice to come back to see beautiful DC areas. I really miss this area a lot when I'm in Houston. So thanks for the invitation, and thanks for coming to my talk. And I guess I want to talk about a simple element in the continental crust, and that's iron. And I guess lots of people here, maybe not a lot, but work on iron stuff. So, okay. So among the rocky planets in our solar system, Earth is quite unusual for its bimodal topography, and this can be easily seen from any satellite images. And this bimodal topography actually distinguishes Earth's two types of crusts. One is the continental crust, which rises high, and the other one is the oceanic crust, which sits low. So this bimodal, this continental crust is actually the Earth's crust is actually in isostatic equilibrium. So this difference in topography actually reflects the difference in crustal thickness. The continental crust is much thicker than the oceanic crust. The oceanic crust is only about 7 kilometers on average, and the continental crust ranges from 20 to 70 kilometers. So this bimodal topography of Earth has been known for a while, but why the continental crust is so much higher and so much thicker than the oceanic crust is actually not very well understood, and it's tied to one of the fundamental questions about the continental crust, and that is how the continental crust formed. So, after decades of exploration, we also know that Earth's continental crust has a very distinct composition. There are a lot of granites in Earth's continental crust, but granites are very rare in the surfaces of other rocky planets in our solar system. And we can tell that just by looking at the MgO content of these rocky planets in the solar system. For example, Mercury, the average MgO content of Mercury's surface is more than 15 weight percent. It's mafic to ultramafic. And if you look at Venus, it's about 10% MgO. It's also mafic to ultramafic. If you look at Mars, it's about 9 weight percent, pretty much the same as Venus. And if you look at Earth, the oceanic crust has about 10% MgO content, but the continental crust has a much lower MgO content. That's about 5 weight percent for the bulk continental crust. And if you look at the more differentiated upper continental crust, it's even lower. On average, it's about 2 to 3 weight percent. So apparently, you need some substantial differentiation processes to get to this very low MgO content, to get to this granitic rock-rich continental crust. So what is the question is, what's the differentiation mechanism? Speaking of the igneous differentiation, there are actually two major differentiation series on Earth. One is this iron enriching series, which we also call the tholeiitic series in the textbook. And the other one is this iron depleting series, which is known as the calc-alkaline series. I guess there's no need to worry about these jargons here, what is a tholeiitic and what is the calc-alkaline. The basic difference is it's all about iron. One is iron enriching, and the other one is iron depleting. And it turns out it's also interesting that these two different igneous series are associated with specific tectonic settings. For example, the iron enriching or the tholeiitic series magmas are mostly seen in mid-ocean ridges and island arcs. And if you look at the iron depleting magmas, they're mostly found in continental arcs and continental collision zones. So you may ask, while both the island arc and continental arcs are subduction zones, they're all arc systems, why are they so different? Why are island arcs more like mid-ocean ridges? So if you look at the data here, these are just compiled data, and I'll be using this simple iron versus MgO content quite a lot in the slides. And these are actually average differentiation trends. And we have the mid-ocean ridge trend, the Mariana Island arc trend. Mariana is a very typical island arc, and also the Andes. Andes is a continental arc. So if you look at these three different trends, they all start from pretty much the same iron content at high MgO. So MgO is an index or a measure of igneous differentiation. And they start with pretty much the same iron content in these primitive compositions, but then it started to separate as they differentiate. And mid-ocean ridge trends and this Mariana Island arc trend, they all show this increase in iron content with decrease in MgO content. And this is what we call the iron enriching trend or the tholeidic trend until they hit this, finally they hit this magnetized saturation, and then they show this rapid decline in iron content. But if you look at the Andes, it shows this continuous iron depletion, right start from the almost the basaltic of highly mafic composition. And that's the major difference between the tholeidic and the calcalcline, or the iron enriching and iron depleting trends. So what do island arcs and continental arcs look like? This is the Circum-Pacific fire zone. There are a lot of arc systems in the Circum-Pacific fire zone. For example, in the, on the west side, we have, on the west side, we have a lot of island arc systems. This is Mariana Island arc system. And the volcanoes in the Mariana Island arcs are very low elevation. You don't see a lot of giant volcanoes there. But if you look at the east side of the Circum-Pacific fire zone, like in the Andes, things are so different. The volcanoes in the Andes arc, Andean arc, are giant volcanoes. Actually, the highest elevation volcano is in the Andes, and the average elevation there in the Andes is about 4,000 meters. So lying behind this dramatic difference in volcano topography or elevation is the crustal thickness. The Mariana arc, the crustal thickness is about, on average, is about 14 kilometers, which is not much thicker than an oceanic crust. But if you look at the Andes, the crustal thickness is from 40 kilometers to 80 kilometers. If you look at the central part of Andes, that's even thicker, from 60 to 80 kilometers. So by definition, an island arc forms when an oceanic crust subducts beneath another oceanic crust, and a continental arc forms when an oceanic crust subducts beneath a continental crust. So the island arc crust is usually very thin. For example, Mariana is only 14 kilometers, but continental arc is usually built on very thick arc crust, like the Andes, 40 to 80 kilometers. And actually, this crustal thickness exerts a major control on the magma differentiation style or the differentiation mechanism. So back to this iron magnesium plot. And here, if we put all global arc data in here, and we group them by the average arc crustal thickness, here we have, again, this is the mid-ocean ridge trend, and then we have this 0 to 25 kilometers thin crust arcs, and then we have this 25 to 50 kilometers normal arc crust, and then this 50 kilometers to 75 kilometers thick arc crust trend. You will see that they all start from the same iron content. And then with increasing crustal thickness, the arc data really transitions from more like a more iron enriching to this Andes like iron depleting trend. So there's a nice correlation between arc magma iron depletion and arc crustal thickness. And this is just another way to look at the correlation between arc magma iron depletion and crustal thickness. Farner Lee, they use this local elevation here, which is actually a measure of crustal thickness. The thicker the crust, the higher the elevation. Assume there's an isostatic equilibrium. And they only looked at FeO content or total iron content at 5% MgO. So they're comparing everything with the same differentiation degree. So you see that there's a nice negative correlation between this iron content and the elevation. samples from the high elevation areas where the crust is thick tend to show this stronger iron depletion. So that's another way to look at the global arc data. So we can say that not all arcs are alike. Usually we say that you find the calcalcline, you see the iron depleted rocks from arc systems. But actually, if you look at island arcs like the Mariana, it's dominated by iron-rich rocks or tholeiic series differentiation. It's only in the Andes where the crust is super thick where you can find a lot of calcalcline or the iron depleted arc differentiation series. So why is there a correlation between arc magma iron depletion and crustal thickness, and why do we care about this maybe iron depletion or versus iron enrichment in the first place? Because if you plot the continental crust here in the same diagram, this LCC is lower continental crust, MC is the middle continental crust, UCC is upper continental crust, and this is the bulk continental crust. They plot beautifully on this iron depleting trend represented by this Andes differentiation series. So we say that the continental crust differentiation features this strong iron depletion. So then the question is, where is the missing iron? Why is the continental crust so depleted in iron? And what's the mechanism that drives iron depletion in arc magma differentiation? This question about iron, on one hand, is related to, may help us understand ultimately how the continental crust formed. And on the other hand, because iron, is related to, iron actually determines the redox states of magmas. So iron determines which in turn, iron determines the oxidative weathering capacity, because that ferrous iron-rich crust will consume more oxygen during chemical weathering. And also iron, because iron determines the oxidation state of magmas, it controls the volatile species in magmatic degassing and may be related to a lot of ore forming processes, for example, porphyry copper deposits, right? So there's a standard view for this iron depletion mechanism or the iron depleting differentiation series, and that's early magnetite fractionation. But there is a serious problem with this magnetite model or magnetite hypothesis. And we know that the chemical formula of magnetite is Fe3O4. So there are 3 iron in each magnetite formula. Among the 3 irons, 2 of them are actually 3+, the ferric iron. So magnetite is a very ferric iron-rich mineral. If you keep fractionating a ferric iron-rich minerals from the magma, you will cause magma reduction, right? There's not much ferric iron in the magma anyway. If you look at basalts, for mid-ocean rich basalt, ferric iron to total iron ratio is about 0.1 or 0.12. If you look at arc magmas, maybe higher, it's like maybe around 0.2 or something. But still, ferric iron is much less than ferrous iron. So there's not much you can do by just depleting the magma of the ferric iron, and you will cause magma reduction. And that's not consistent with what we see in these iron-depleted arc magmas. Because those iron-depleted magmas, they're usually highly oxidized, which means that the ferric iron to total iron ratio is pretty high. So that's the major problem with this magnetite hypothesis. So apparently, magma iron depletion happens in the crust. It's by intracrustal differentiation. So whatever the process is, whatever the mechanism is for this iron depletion, we think it must explain these 2 important observations. First of all, why does arc magma iron depletion correlates with crustal thickness, and also needs to explain the high oxygen fugacity, that is, the high ferric iron to total iron ratio in these iron-depleted magmas. So I've been talking about this crustal thickness control on arc magma iron depletion. What does crustal thickness do, actually? The crustal thickness controls the average igneous differentiation pressure. And this pressure can have a profound impact on the mineral assemblages that crystallize or fractionate from the magmas. This is the phase diagram constructed by Green et al. In 1982. It's actually a very old phase diagram. I really don't have much experimental stuff to show here. I'm sorry. I know a lot of people here are experimentalists, but this one is really a very important concept from an old phase diagram constructed purely from experimental work. And so this is a basaltic system, hydrous basaltic system, and it looks a little messy, but we don't really need to go through all the details in here. This is the liquiders, and this is the soliders. So let's focus on this 1,000 to 1,200 degrees range, because that's about from basaltic to andesitic differentiation, and that's the range that we think about magma differentiates from basalt to andesitic composition that really separates the iron-enriching and iron-depleting differentiation series. So if you look at the y-axis is pressure, we start from the low pressure differentiation or the fractionating phases. It's dominated by plagioclase plus pyroxene and olivine. And if you increase the pressure a little bit, plagioclase is gone. You have olivine plus pyroxene. If you further increase the pressure, it's pyroxene. And you increase the pressure to above 1.5 GPa, you get garnet. And it's dominated by crystallizing phases, or the residual phases are dominated by garnets plus cyanopyroxene. So if you look at the iron content of these minerals are fractionated from the magmas. Plagioclase has no iron, so we call it an iron-free mineral. If you look at olivine and pyroxene, these minerals, they have iron, but they actually like magnesium more than iron. So they have iron, but they're not super rich in iron. We call them the iron-bearing phases. If you look at garnet is completely different. It's really iron-rich phase, really likes iron. So theoretically, just from this phase diagram, when you increase the pressure, the fractionating or residual phases transition gradually from this iron poor to iron-rich. So we can predict that just from this phase diagram. When you increase the pressure, when you increase the crustal thickness, you should get more and more iron-depleted magmas by differentiation, right? And also from Green's experimental work, we can also predict that at the high pressure, garnet is really the driver of iron depletion. So you may say that why we don't see a lot of garnets in andesites, right? We have olivine, plagioclase, and pyroxene phenocrysts in andesites, but garnets are usually very rare. But this is an example of garnets in andesites from New Zealand. The reason for this lack of garnets as phenocrysts in these andesites, as Bach et al. Suggested, because garnet is not stable at low pressure. So your magmas really need to ascend fast in the crust without too much shallow level differentiation to preserve the garnets from great depth. So even if we don't see garnets in these andesites, we still can tell them they exist in the deep roots of the continental arcs by just looking at the chemistry, here especially the rare earth elements, right? Garnet has this very diagnostic signature in fractionating rare earth elements. The garnets prefer the heavy rare earth elements relative to this middle rare earth elements. So garnet fractionation will cause magma, cause this increase in dispersion turbulent ratio in the magma, right? So if iron depletion is driven by magnetite, then you should not expect to see such a correlation because there's not much rare earth element in the magnetite anyway. And if iron depletion is really driven by, let's say, amphibole, you would expect to see the opposite because amphibole does the opposite. Amphibole prefers the middle rare earth elements relative to the heavy rare earth elements. So here, let's look at the global arc magmas. We're looking at only the arc magmas with 4% MgO. So here, although I plot the FeO content divided by MgO, MgO is actually a constant. The denominator is a constant. So this really just reflects the depletion in iron at 4% MgO content. and acidic arc magmas. And there's a nice negative correlation between arc magma dysprosium ytterbium ratio and iron depletion. So the most iron depleted andesites have the highest dysprosium ytterbium ratio. And that's perfectly consistent with Garnet fractionation driving this iron depletion in arc magmas. So you may ask, so far we only looked at the arc magmas. Do we have any samples from the deep roots of the continental arcs so we can see what's going on there and what's the mineral that really sucks out iron from the magma? These samples are actually very rare at the surfaces because they're so deep and they're so dense. It's not easy to bring them to the surface, but we were lucky to get some from central Arizona. And these are garnet proxenites. They form at 60 to 80 kilometers deep. And these cumulates, these deep arc cumulates, are really rich in garnets. And these reddish, pinkish minerals, these are garnets. And the greenish are the cyanopyroxenes. And they don't have any plagioclase because they formed so deep and high pressure is so high, plagioclase is not stable. And they have a range in Mg number, which is a measure of differentiation from 0.8 to 0.4. And Don Anderson coined this name arclogite for these deep arc cumulates because I think this is a very elegant name for this kind of accumulate. You know, on one hand, it has the same mineralogy as eclogite, right? Garnet plus pyroxene, but it formed in a different way. It's of an igneous origin. So he called it arclogite, arc plus eclogite. It's not an eclogite, but it has the same mineralogy as eclogite. And if we plot this arclogite, these deep arc cumulates, continental arc cumulates, and it's a FeO, MgO plot, together with the Andean magmas, which is iron depleting series, they have this high iron and high MgO content, which perfectly balance or are complementary to the iron depleting magmas found in these continental arcs. So actually, this garnet-driven iron depletion hypothesis was first proposed by Trevor Green and Ted Ringwood. Ted Ringwood is one of the fathers of modern experimental petrology. It's really amazing that they already thought about this back in the 1960s. They were actually inspired by some garnets in andesites or garnet-bearing andesites from Victoria, and then they did some experiments and showed that when you increase the pressure, you can actually get the iron depleting differentiation series. But they didn't really do much about this idea, and it's unfortunately this Garnet hypothesis was then largely forgotten by the community, and it was then dominated by this magnetite hypothesis. But I think this is really amazing because, in the 1960s, the plate tectonics theory was just accepted, right? We don't really know much about the continental crust. You can't really say much about this iron depletion versus iron depletion, how important they are, because we don't really know the continental crust composition at that time. But what Green and Ringwood didn't realize in their early work is that the garnet has its redox effect because garnet really likes the ferrous iron relative to ferric iron. What I show here are the whole rock iron content of these cumulates and also the ferric iron to total iron ratio, or you can call it iron valence in this accumulate garnets. And then this reconstructed bulk silicate ferric iron to total iron ratio in these cumulates as a function of their Mg number. So you can see that this garnet, there's really not much ferric iron in these garnets. The iron in these garnets are almost a pure ferrous iron. And because of that, because garnet is the major iron-bearing phase in its cumulates, it makes that the bulk silicate parts of the cumulates are dominated by ferrous iron. And they all have this lower ferric iron to total iron ratio than even mid-ocean ridge basalts. So it must be even lower than island arc basalts, right? So if you keep fractionating these iron-rich cumulates, but ferric iron depleted cumulates, you will start to increase the ferric iron to total iron ratio in the magmas, and you start to oxidize the magmas. So before we talk about this, come to this conclusion about magma oxidation caused by this Garnet proxenite fractionation, we need to think about the oxides, because especially magnetite, because magnetite is such a ferric iron-rich phase. Even a small amount of fractionation of magnetite will probably deplete all the ferric iron in the system, right? So we can look at the oxides in these cumulates. These are the backscattered images of these cumulates, and these bright phases are the oxides. You can also tell that from the titanium content in these cumulates. These oxides are mostly rich in titanium oxides. It turns out that the oxides saturate very late in these cumulates. They're kind of very low titanium oxide content in this high Mg number primitive cumulates, so that you don't see a lot of these oxides in these primitive cumulates. But start to increase as Mg number drops to about 0.6 in these cumulates. But what's interesting is that these bright phases, these oxides, they're dominated by rutile with lesser amount of yeomanite. Actually, there's actually no magnetite in these cumulates. So that basically says that magnetite probably contributes very little to iron depletion in its calc-alkaline magma differentiation. But why is that? Why is magnetite undersaturated throughout the differentiation of these deep arc magma differentiation? And that's also because of pressure. And we mapped out the magnetite saturation fields along the iron enriching and iron depleting differentiation series under various pressures and oxygen fugacities. We found that as you increase the oxygen fugacity, your magnetite saturation field does expand. But when you increase the pressure, the magnetite saturation fields start to shrink. And let's just focus on this middle panel. This is about the calc-alkaline series. And if you increase the pressure to about 1.2 GPa, you'll never saturate the magnetite, even if I push this oxygen fugacity to FMQ plus 3, which means it's very oxidized the system. Usually arc magma is about FMQ plus 1, plus 2, or something like that. Plus 3 is already very oxidized. So that's the pressure effect on magnetite saturation. It's actually not surprising given that magnetite is a spinel group mineral, right? We know that spinels, they don't like high pressures. And actually, we don't see any spinels or magnetite in most eclogites. So crustal thickness controls magma differentiation pressure, which in turn controls not only iron depletion versus iron enrichment in the magmas, but also controls this redox evolution of magmas. In a thin crust, which is the case for island arcs, the pressure differentiation pressure is low, you will hit magnetite fractionation or magnetite saturation late in the differentiation, and then it starts to deplete ferric iron system and causing magma reduction. But if you look at the thick crust in the continental arcs, where the pressure is high, and then your magnetite gets destabilized, but your garnet is stabilized. And then garnet fractionation depletes this ferrous iron in the system, but let the ferric iron pass through, and this will cause magma oxidation. And we call this Garnet redox filter effect. But do we see any evidence for this Garnet redox filter effect? And yes, we do. And the evidence comes from the europium in its cumulate minerals. We looked at the europium anomalies in the cumulate clinopyroxene and cumulate garnets, and we plot the europium anomalies in these minerals against the Horak Mg number, which again is a measure of differentiation. So if you look at this high Mg number cumulates, these minerals all have this slight negative europium anomalies. Why is that? It's because europium is multivalent. And it's mostly in europium 2+ and 3+ in the system. But europium 2+ is actually much more incompatible than europium 3+. So that means europium 2+ does not like going to the pyroxene and garnet. So when your system is relatively reduced, you have a lot of europium 2+ in the magmas. And they don't go into the pyroxenes and garnets, and that's causing the slight depletion in europium. In europium, there's a negative europium anomalies. But if you look at the low Mg number accumulates, the europium anomaly the europium star ratio starts to go back to 1. And that means you can only have this when you gradually oxidize the system, and that really gets rid of the europium 2+, and then all the europium can go into the minerals, just like other 3+ rare earth elements. This last panel is just the averages for europium anomalies in these pyroxenes and garnets. And based on this idea, we can construct this redox evolution path for these cumulates, or as these cumulates crystallize and fraction from the system. We found that the system, your highly basaltic primitive arc magma, start with actually quite reduced conditions. And then it starts to increase. At the end of differentiation, it reaches at least about FMQ +1 or +2. So that means with the differentiation, with the fractionation of these cumulates, the arc magma was oxidized by at least 2 orders of magnitude. Well, you may say that it's actually quite debated about this initial redox conditions of arc magmas. And I'm not sure if I can really give you a very strong argument about the initial redox conditions of arc magmas. But in this case, it seems that it starts with the reduced condition and becomes oxidized with fractionation of this garnet-rich, this ferrous iron-rich cumulate. So that's about iron in a system. That's about iron depletion in arc magma differentiation. And if you recall the oxides in the cumulates, there are actually tons of rutile in the system. That actually may help us to solve another problem about the continental crust. It's been known for a while that the continental crust seems to have a lower niobium-tantalum ratio than basalts. We have mid-ocean ridge basalts here and ocean island basalt here. And niobium-tantalum, these two elements we call them geochemical twins. They have pretty much the same or identical chemical properties. So they don't usually fractionate from each other a lot. But we have this mysterious low niobium-tantalum ratio in the continental crust. So if you agree the subduction zones are the primary sites for continental crust production, and we do see a lot of low niobium-tantalum ratio arc magmas, then the question is when and where do these arc magmas acquire these low niobium-tantalum ratios? So here, first we can look at arc basalts. But what we found interesting is that the arc basalts actually have pretty much the same. The first row is for mid-ocean ridge basalts, and the second row is for arc basalts, for niobium-tantalum concentrations, and then niobium-tantalum ratios. We found that most arc basalts actually have almost the same niobium-tantalum concentrations and also niobium-tantalum ratios as mid-ocean ridge basalts. It's kind of surprising because we have a lot of crustal recycling and subduction of surface or upper crustal materials to arc magma sources. But this does seem to suggest that this low niobium-tantalum ratios seen in many arc magmas is not the source signature. It's not caused by subduction of upper crustal materials. So it must be developed in a differentiation stage. And then we look at this average differentiation processes. And then this is something interesting that we found. We plot global arc magmas based on the average crustal thickness. We group them by this thin and normal crust arcs, and then this very thick arc crust. And then you see that for the thick crust arcs, the niobium-tantalum ratio starts to decline rapidly after the silica content reaches about 60 to 65 weight%. But if you look at the thin and normal arc crust, this trend, niobium-tantalum ratio is almost constant and only starts to decline after it becomes highly differentiated, after the silica content reaches more than 70 weight%. Now, these are just the average differentiation trends. You can also look at the histograms for niobium-tantalum ratios in these felsic rocks from thick crust arcs and then thin and normal crust arcs. And there is a systematic shift in this niobium-tantalum ratio from thin and normal crust arcs to this thick arc crust. In the thick crust arcs, these felsic rocks have systematically lower niobium-tantalum ratio than the felsic rocks from thin and normal crust arcs. And we also plotted niobium-tantalum ratio in these felsic arc rocks versus their dispersion ytterbium ratio. And again, this dispersion ytterbium ratio is a signature or is a measure of Garnet fractionation. Garnet fractionation tends to increase the dispersion ytterbium ratio. And we found that there's an interesting negative correlation between this niobium-tantalum ratio and dispersion ytterbium ratio. That means your Garnet fractionation, the magmas that see the most Garnet fractionation, they tend to show this low niobium-tantalum ratios. So that means there must be a phase that really likes high pressure that fractionates niobium-tantalum in the continental arc. And that's probably the oxides. And these are, and then we test this. We then test this hypothesis with the same cumulates from Arizona, because just from the data survey, we can predict that in thick crust, there must be a reservoir with high niobium-tantalum ratio to balance the low niobium-tantalum ratio in the differentiated crust. And then that's why we looked at this Arizona cumulates. So again, titanium is a measure of oxide fractionation. When you have oxide saturated, you start to see this titanium to increase. And coupled with this titanium, we see this increase in niobium and tantalum concentrations. They increase by almost up to 2 orders of magnitude as titanium rises. But what's interesting to me is that before oxide saturation, this niobium-tantalum ratio is highly variable, but the average is close to this basalt value. But once you hit this oxide saturation, then most of the samples have systematically higher niobium-tantalum ratio than basalts, which is good, right? Because these oxide-bearing deep arc cumulates, they may balance the low niobium-tantalum ratio continental crust. And then we know that the oxides are dominated by rutile. So it must be rutile that really fractionated niobium-tantalum in the magma and also caused this high niobium-tantalum ratio in the cumulates. We then measure these rutiles in situ by laser ablation in the cumulates. And the data actually confirmed our speculation. This is the histogram of niobium-tantalum ratio and the rutile and also the iron titanium oxides. The rutiles are systematically higher than the average basalts. That actually testified the hypothesis that rutile is the phase that controls niobium-tantalum, and rutile is the phase that causes niobium depletion relative to tantalum in the continental crust. Sure.
Don't all experiments show that rutile?
Yeah, that's a good question. Actually, it's quite debated. I would say that the latest, if you look at the latest work by Xiong et al., they argue that actually low temperature, less than 1,000 degrees C, and in a water content, when the water content in the system is less than 10%, it starts to flip. The D niobium over D tantalum starts to flip. But I don't think their experiments are that precise to show large error bars, but at least that's what they argue. But what I think here is that I actually don't know the answer, but at least just from the natural samples, we actually see the opposite. The niobium-tantalum ratios in these rutiles is actually higher than basalts, which means you do need a D niobium over D tantalum higher than 1. But why is there such a discrepancy, big discrepancy between the experiments and the natural sample data? I actually don't have a good answer for that. I guess there's need for more experimental. So that's my current, yeah. But then the question is, why we only see this rutile signature? Why we only see this low niobium-tantalum ratio in thick arcs, in thick crust arcs, right? It's actually also explained by the pressure effect on rutile saturation. Rutile really likes high pressure. So if you want to saturate rutile from moderate differentiation arc magmas, for example, 68% silica, you really need about at least 1.5, 1.7 GPa to stabilize rutile, right? So it's only possible. So 1.5 GPa is about 40, 45 kilometers thick crust. So you can only do that in a thickened crust arcs like a continental arcs. And in island arcs where the crust is thin, your rutile saturation is significantly delayed, and it can only saturate at relatively low pressure because the temperature gets lower in a highly differentiated magmas. That's why you see this dramatic difference in this rutile saturation between continental arc magmas and island arc magmas. That's all due to this pressure effect on rutile saturation. So I think the low niobium-tantalum ratio, the missing iron problem, they all point to the same story. That's you really need a crustal thickening. It's all about crustal thickening. It's all about pressure effect on magmatic differentiation. So to summarize, arc magma differentiation transitions from this iron enriching trend to iron depleting trend with increasing crustal thickness. And Garnet fractionation is like we call it an iron or a redox filter at the base of magmatic origins. It depletes the ferrous or the 2+ iron in the system, but let the ferric, the oxidized iron, to pass through to the shallow crust. And it does cause some redox effect on the magmatic differentiation systems. And then this rutile crystallizes at high pressure. It causes this low niobium-tantalum ratio of the continental crust. So now we may come back to the question that I asked at the beginning of the talk, why the continental crust is so much thicker and higher than the oceanic crust. We think that perhaps just about every piece of the continent was generated by these orogenic processes. But then another interesting question is why the continental is on the average continental crust is only 35 to 40 kilometers. It's significantly thinner than what we've seen in the Andes. It's because you have a lot of processes to make a thick crust thin, right? You have this gravitational collapse, you have erosion of the surface. All these processes tend to make a crust thin. They tend to destroy a thick crust. So perhaps 35, 40 kilometers, just the thickness of continental crust, mature continental crust at rest. So you have to produce continental. You have to start with a much thicker continental crust during production. So if we follow, Campbell and Taylor, they wanted to emphasize the importance of water in making granites and making continental crust. They had this paper with this very catchy title: "No water, no granites, no oceans, no continents." If we follow that style and make our own title in their way, we say no garnet, no iron depletion, and no origins, no continents. I guess that's the most important take-home messages for you. Thank you. Hey, Bob.
Hi. Hi. So I know you focus on garnets, but there's a puzzle to me because garnets very easily take in both ferrous and ferric iron. And so the question to me is not what is the iron taking up the ferrous iron, but what is it in the shallow crust that's retaining ferric iron? Because otherwise it would seem to me the garnet would reflect the average crustal composition since you can take both.
I'm not sure if I understand the question clearly.
You're saying the garnet that's basically fractionated.
complicated because you may have crustal assimilation. In island arcs, you can assimilate a lot of seawater. You have sulfate in modern seawater. That's going to mess up all your redox process, redox state in the magmas. If, Mhm. Uh, I'm not sure if I agree. So, yes, my understanding is that in arc systems, the carbon dioxide, water, they don't have much to do with the redox in buffering the redox conditions. The sulfur does that because yeah, sulfur has 8 electrons to play with. The sulfur there's only like 1,000 ppm sulfur in basalt. In felsic magmas, you have only a few hundred ppm sulfur. So you're talking about a few hundred ppm sulfur versus 4% something iron. So even iron has only 1 electron, but in the end, it will maybe have pretty much the same potential in controlling the redox conditions. So ultimately, it's like an interplay between iron and sulfur in the system. In that sense, I agree with you, yeah. Yeah, sure, that's definitely true. Uh, I think first of all, if you look at the magmas from the Andes, you can tell directly from the trace elements like rare earth element to say that there is garnet at the base of the Andean arc crust, because otherwise, I mean, either by fractionation or by pre-melting, I mean, otherwise you can't really fractionate rare earth element in that by increasing the dysprosium and terbium ratio. You can't do that by amphibole. You can't do that by any other minerals. So this is from magma perspective. And in terms of the samples, there are actually a lot of debate whether these are pristine cumulates or these are metamorphic rocks or how much trapped melt in these cumulates. Sure, there's a lot of debate on that. I guess my argument would be that many of our samples, they do show this cumulate textures. And also, if you look at the major elements, they show this a complementary composition trend. I mean, a composition that's complementary to magma differentiation trends. For example, they have very high iron content, they have very high titanium content, but in the magma differentiation, you basically have basalt to granite, right? You start with 10% iron, but these cumulates, they have 10 to maybe 20% iron in there. Unless you have a very substantial open system processes, it's very hard to, increase the iron content in these rocks by this much. I guess that's my argument. Thank you.